Hello, everybody, and welcome to episode 90 of the Hyperthesis podcast. I'm Liam.
I'm Pheely.
I'm Patrick.
I'm Duncan.
As you can hear, we have another very special guest with us today, Duncan Osmond. Thanks for coming, Duncan. It's great having you.
Yeah, thanks for having me.
So we all completed our undergraduate degrees together at St. Francis Xavier University. Like a lot of the guests we've had, we went to university with them at one point. So Duncan, you did a physics degree at the same time we did. So just a little kind of background on Duncan. He received his undergraduate in physics from St. Francis Xavier University, like I said, and then he went on to complete his master's degree in physics. Was it in physics?
Yep, it was in physics. Yep.
Yeah, so you complete your master's in physics at the University of New Brunswick. During your undergraduate, you did research and worked with Dr. Jacob Levman on novel reconstructions of biomedical MRI data. And during your master's work, you worked with Igor Mastikin. I'm not sure if I pronounced that correctly or not.
Oh, very good.
Okay, I tried my best. Igor Mastikin on experimental MR pulse sequences to extract information about the dynamics of spray systems. And now you're currently a systems engineer with the Naval Engineering Test Establishment in Halifax, Nova Scotia. So that's quite the career change. Well, I think it is, at least. So we'll come to that later. So thanks again for joining us. But before we get to you and ask you many, many questions, do we have an intro topic today?
Yes. I have a fun little intro topic. The last few episodes have been quite physics heavy, so I thought I'd swing it back to a different topic just for the intro. We like to gear our intro topics towards what our guest is talking about, but in terms of NMR and magnetic resonance, there is a lot going on, but I'm excited to delve into it more so with Duncan himself. So as an intro topic, I kind of want to talk about a little bit about climate and a specific person. So a couple weeks ago, I was at a very interesting talk by a former graduate, and I'm talking about I think he graduated in the 60s or late 50s from my department. But he moved up the ranks in climate science and eventually was part of the NOAA in a very top position among other different American Institute positions trying to measure climate change and the climate and doing a lot of that kind of research. So this person is Dr. Russell Schnell, or Schnell. He's an alumnus from the University of Alberta, and before it was even called the Department of Earth and Atmospheric Sciences, and I think it was just the Department of Geology at that time. But he was the deputy director of the NOAA. So for those that don't know or aren't familiar with the American associations, it's the National Oceanic and Atmospheric Administration. So, I mean, pretty big guy. He was deputy director of the Earth System Research Laboratory's Global Monitoring Division, based in Boulder, Colorado, and he is now a senior scientist with the Cooperative Institute for Research in Environmental Sciences at the University of Colorado. So he doesn't have a lot of ties to the University of Alberta, but he was invited to give a lecture, and I think there's a scholarship named after him here as well. And he shared over the course of about an hour just kind of insights from his work and his experiences in climate change and trying to actually measure the climate. But he had two pretty wild stories that I just wanted to share. I don't think they should be something that's just kept in a room full of people. So the first story is that he did a lot of research in Russia. So Russia is really interesting. There's quite a lot of land cover, especially in northern regions. So it's really interesting to see how it changes. Canada itself is also interesting, but at the time when he was doing this sort of research in Russia, it was kind of around the end of the Cold War, collapse of the Soviet Union. all of that fun stuff happening. And so around the collapse of the Soviet Union, there was essentially a lot more freedom to kind of go into the country and work with different militias after it had broken up. And so Dr. Schnell was able to go to kind of the northeastern part of Russia to conduct a months-long research campaign there. So they were looking at a lot of things, including just kind of changes within permafrost, which is very prevalent up there. But there's still a lot of different things that you have to deal with when you're up in Russia, including dealing with these militias and paying people off so that you could go do your research, along with dealing with, say, the KGB, which was dying but still around and kind of transferring. And so as he was telling the story, he says, well, the CIA sent us over because apparently when you work for one government agency as a climate scientist, other government agencies are interested. So the CIA sent him over along with some other institutions, and he had a briefcase filled with $40,000 in small bills so that he could pay off people to like book flights or I guess charter flights with the then dysfunctional Russian military and just things like that.
Well, $40,000 then, is it what is it equivalent to now? It's like $500,000 or something that much?
Let me check, but I mean, it's certainly a lot. And the fact that they needed it in small bills too, it is pretty wild, but that's what you needed to pay people off. And you could certainly get a lot done. So $40,000 in 1990 is worth just under $100,000 today. And that's, of course, American dollars. So it's, crazy that they brought that. So they were actually able to get flights going. They could get food. They could get the resources they need. And then suddenly the KGB caught wind of what they were doing. So while they were in a Russian military plane, they were told that if they landed, they'd probably be arrested. So he got that plane redirected, flew into Anchorage, Alaska, or somewhere in Alaska. It might have been Juneau, one of those areas, which is insane because the Americans didn't know they were coming. They were in a Russian plane, and it was able to sneak past any border security, and they didn't know it was coming until it landed. So he walks out of the plane, and it's just surrounded by police cars and a whole bunch of military people and all that. And it's like, oh, what's going on? Oh, right, that Russian plane. So, I mean, that's field work to the extreme. But another interesting thing that Dr. Schnell was able to do in Russia was look at a very peculiar phenomena. So during his time in Russia, he was exploring changes in permafrost, and there's something like essentially when permafrost becomes explosive, so it starts to melt, which may release a lot of methane, and because it's melting, the ground is shifting. So you can actually, there are craters all scattered throughout northern Russia where this permafrost has melted and the ground has shifted. And if you get the right minerals that are there, like flint, it just creates a spark and boom, massive explosion, leaving a crater. But during his research with that, they were also interested in looking at this strange plume that was coming from an island north of Russia. So it was still a Russian island, and we call it Bennett Island, but in Russia it's called Ostrov Beneta. Apologies for the pronunciation, but it's a very northern island. I think it's something like 76 degrees north. But what they noticed from very basic preliminary satellites was that there was this plume coming from it. And so the Americans were convinced that the Russians were doing some sort of nuclear testing there, or some sort of radioactive stuff, something to do with nuclear, essentially, on this island, which was generating this plume. Now, they were able to do research and actually fly over the area and determine that based on samples collected from a plane flying over the plume, and in this, again, it's a massive plume. If you look up Bennett Island on Wikipedia, you can actually see an image of it. It's huge, but they flew over it, and instead of it being smoke or containing radioactive contaminants that would be indicative of some sort of nuclear research, it was water vapor. So this island has the perfect set of mountains, and when the wind hits it just right, it takes this very, well, I guess more humid air, launches it straight up into the atmosphere where it cools, and then it creates this plume. So if you get a steady wind over there, you'll see this plume generating. There's a lot more science in there. But the final thing that I want to tie into with something a bit more modern is that during Dr. Schnell's talk, he was discussing kind of how the ocean itself covers 70% of the surface of the Earth. And so it's responsible for absorbing so much carbon dioxide. It's responsible for the heating, so that it's really the ocean we have to be more concerned about in terms of global warming and climate change, more so than the surface of the Earth, because it has a lot higher heat capacity. I mean, a fun fact from that is that if you dig a couple hundred meters underground, it's still cold. And then it starts to get warm as you go deeper, but it's cold around that area from the last ice age. So the changes that we're seeing are really coming from the ocean. So there was a really interesting study that was published in Nature just not too long ago by Weilei Wang and others, which went on to use measurements on a global scale to try and figure out exactly how much carbon was actually being stored in the ocean, and more so how much was being sequestered. And from their study, which again took place all over the world, and their focus especially on phytoplankton, which is able to absorb carbon dioxide and convert to sugars, and then when they die, they just sink to the bottom of the ocean. They found that the carbon dioxide that can be stored in the ocean from the atmosphere is about 20% greater than the estimates published in the last IPCC report. So this is pretty groundbreaking stuff, because, I mean, the fact that it's a 20% difference, or 1/5 more of the carbon dioxide that can be stored in the ocean than previously thought, is, I mean that's quite a lot.
I saw that, I don't know how legit this was, but there was like people trying to come up with ideas of like carbon capture, and one of them was making these big tanks full of phytoplankton and like putting them in places. And I don't know, it feels pretty like inefficient to me. If you want to like do mass carbon capture, but maybe I'm just missing something.
Yeah, I mean that certainly something that's being tested, but when you're dealing with, I mean, it's just the scale
Yeah.
of the things, because think about how big the oceans are, and they can capture quite a bit of carbon. So it's about 15 metric gigatons per year that the ocean can store, which is an increase of 20% from the previous estimates, which was about 11 gigatons. So, but like trying to work on these small scales is just, I mean,
Yeah.
we could get into carbon capture, but that's
Feels like if you want to do carbon capture, you need like a really, really big device / plant or something. You can't just like it's like, we can't just like plant a few more trees in every city. It's like you have to replant whole forests, or else it's not going to make much of a dent.
I have comments on the replanting forest, but we'll move on. So the study really kind of redefined how we can look at the ocean's role and phytoplankton's role in terms of carbon capture. And I mean, that's what's happened before, is the fact that we have oil because of dead phytoplankton pretty much in the ocean that then sank and then was compressed and changed forms into what we now see as oil. But it's important to stress from the study is that the absorption process takes tens of thousands of years to happen. So it's not a sufficient solution for like solving climate change, because we're pumping far more than that. And so it's just interesting to know that, okay, they are taking in more than we thought, but one, for how long, and two, for I guess how much can that still be maintained, especially as the ocean is becoming more acidic, and then it's destroying more things. So there's really like a lot of carbon capture will not be the solution. So it's interesting to know that the ocean's doing even more than we thought. But for now, it's, not even a drop in the bucket. So, we're spitting out tens of gigatons every year. I think it's something like 50 or 60 gigatons of CO2. So, yeah, nowhere near close. But very interesting research. Lots of cool modeling that went in, and then use of different remotely sensed data. Just a final thing on your comment, Liam, is people are actually looking at dumping iron powder into the ocean as a fertilizer for phytoplankton to absorb more carbon dioxide. But it also causes issues because it takes oxygen out of the water itself because of the whole decaying and dying process. So you remove carbon dioxide from the atmosphere, but you also make the water unlivable.
Yeah, I was gonna say, like, if I had a fish tank and I just poured a bunch of, iron shavings into it, I feel like the fish wouldn't be too happy.
Exactly.
So, yeah, they probably, that's like an idea though. Maybe that'll help lead to better, less deadly developments.
Well, people sink ships, right? Like to be like a substitute for corals, and I think have been working pretty well, especially those like decommissioned ship. It actually might cost more to try to take it apart to salvage it than just, you know what, let's go drop it.
Yeah, like raising a sunken ship out of shallow water is that's like not an easy thing to do, let alone like somewhere in the middle of the ocean. So it's easier to just leave them and let kind of nature reclaim them. And it's also a bit different than like if you have a ship in the water, right? Like there's going to be rust and stuff on it, but it's not like you're spraying a ton of already kind of shaven bits of rust and metal down. It's like it slowly kind of rusts and decays, I think.
Yeah, I was actually just reading an article that they're taking the fastest ocean liner to cross the Atlantic, which hasn't been in service for many years.
The super blue nose.
That's
No.
the one. No,
Yeah,
but
that one, right?
they're taking it and scuttling it off the coast because it acts as like a framework for a coral reef. So it essentially generates more biodiversity in the area, and then as it slowly decays and rusts, that's replaced by like the actual habitats of animals. So really interesting process, and the fact that they're doing it on such large scales is pretty cool.
All right, this is the perfect segue to Duncan. I was like, how am I going to segue this intro topic into talking about, like ships and things like that? So yeah, Duncan, you are thank you, Patrick, for that intro topic. But now it's time to ask Duncan about what he does. So you're a systems engineer with the Naval Engineering Test Establishment in Halifax, Nova Scotia. So I understand that there's some things you're not allowed to talk about for, security reasons, but can you tell us kind of maybe vaguely what you do? What is this? How did you land this job? Kind of things like that.
Yeah. I have to be pretty vague, but generally speaking, I support the current like Canadian naval project, which is the River Class Destroyer project. Yeah, it's pretty interesting. The kind of other people that you see on these sorts of programs are from a really wide variety of backgrounds, but a lot of them are from physics, like a surprising amount. And for a job title that has engineer in it, and definitely not a P-Eng, for something that has engineer in it, there's a surprising lack of engineers in a lot of these like different positions. So it's surprising, I guess, to see that there's a lot of overlap in interdisciplinary work with these kinds of things.
That is pretty interesting, and it gives me hope for if academia doesn't work out for me.
So basically, for people who apply for this job that they say like for engineers, like do you just apply because like even though it's like you're not an engineer, or is it like how does that work? Or was it more like, oh, a person who like, okay, you can apply with this, it's not a big deal if you don't have the exact requirement that they say on paper?
Um, yeah, no, that's a great point. The kind of road that I took to get into the job that I'm at now, was very roundabout. I applied for a pretty different position. I actually, um, my background is in kind of like a very interdisciplinary, like look at like signal processing and very like generalized simulation work. Um, so I was looking for a career as a underwater warfare modeler originally, which is a position that came up here in Halifax. And while I made it pretty far into the interview process, I think they found somebody with maybe a little bit more of a specialized skill set for the role. But um, I guess it's kind of like a testament to like the wide net that like a physics background casts, that they were really really interested in trying to find another spot for me. And then ended up like being offered a job where I'm at right now. So yeah.
So again, I don't know how much you're allowed to say on it, but so can like what? So the whole project is basically Canada's making this new River class destroyer, which is a ship. Um, so you're helping like the process to build that. Are they just making one, or are they making like a multiple? Or
Yeah, unfortunately, I don't think I can comment on that
fair
stuff.
enough, fair enough.
Yeah.
No, understandable. But yeah,
Let's
so
see it like this. Once it's built, we'll see. I mean, it's not like these
yeah,
things. It's not like they can hide these things. Actually, they can, but
Exactly.
it's not very easy to do.
they have these big. I don't know what to call them, but they can hide they can hide ships and components of ships and things pretty well because they have these big like barriers that they surround them with. Like my dad actually worked at the dockyards in Halifax. He maybe well he fixed submarine sonars. He's retired now, but he fixed submarine sonars, so maybe a tiny bit related to the underwater warfare job you applied for. But he was a glorified electrician. And he
Yeah.
he did good job and stuff like that. But I like for submarine sonars or for some not sonars for submarine propellers, right? Like they have certain profiles and shapes that make certain noise in the water, and you don't want the bad guys, or I don't want to say bad guys, but you don't want other nations to know about them so that they know what like sound profiles to look for. So anytime a submarine comes out of the water, they like kind of cover the back half with this big like safe this like tarp slash box so that you don't see it. So maybe they do that for the River class destroyer components, and then one day
Well,
it'll
I
have the
mean,
grand unveiling.
the shape of propeller is top secret, I think,
Yeah,
and
yeah,
yeah, and also like let me put it this way: Canadians will spend a lot of money, a taxpayers' money, or to build something, and if that thing will be hidden for the rest of the time, or like even when it's built, it begs the question what they were building, right? So I mean, if you want to get more naval budget, and you said, well, we can't really show you what we built at all. I mean, in the States, there are shows all the time on the military stuff. So I'm sure once that's built, that's gonna be we will see it.
my
Um,
oh, I was gonna say just quickly, my dad would always make these jokes about like he's like, oh, we're like doing all this submarine work, and I'm like, well, like what's the point? And he's like, well, have you ever seen anyone attack Canada with submarines? And I'm like, well, no. And he's like, well, there you go, because it's all like hidden warfare. So I thought that was kind of funny. Anyway, yeah, I'm always very interested in the like the naval stuff. And I know Pheely's done a little bit of research into like warships and things from a completely different point of view. Um because my dad worked at the dockyards, I'm always like I've got to go down and go on a lot of these big ships. Like they would have like the bring your kid to work day, and I get to go, and there'd be like a British aircraft carrier like the HMS Ark Royal, and we get to go on like a tour of this ship, and it was always so cool. So I'm very interested in like naval engineering and technology and stuff. So it's really cool that a physics degree led you to that.
um, before we get more into that, I will just say it's public information. Apparently, 15 have been ordered at a price of just under $80 billion Canadian. But
Wait, so when you say ordered, you mean like ordered to be made, or because Canada has this bad habit of buying used military assets from other countries, like our submarine fleet, which is all diesel powered submarines. They just kind of bought like the used British ones, I think. So
In this case, it seems like they're being built from scratch.
yeah, or else
in
Duncan
Canada.
wouldn't be here, I
Okay.
guess.
Well, once we get to my story, you might change your mind.
Oh, okay.
But in terms of what you do, I know we can't talk about, so we'll probably be delving back into NMR soon. But just in terms of generally, do you spend a lot of time at a computer, or is it like actual kind of lab testing? Or are you out on the water often?
The specifics of my job or more like desk work for sure.
Okay.
It's I think technically I'm a systems engineer software specialist, I believe is the little addition that's on there. Which is I think kind of how we as physicists get our foot in the door on something that would be traditionally something that's like very strongly engineering focused.
I think it's more about like the transferable skills. So I think I want to move on something that we actually can discuss at length. And so just a little bit of introduction to NMR. Well, we all know the MRIs, machines, the magnetic resonance imaging. So it's what I heard. I don't know if this is true, but back in the days, because NMR is nuclear magnetic resonance, but people were afraid of the word nuclear and to advertise like a device, a medical device with the word nuclear in it is it's nuclear has stigma onto it, right? Like this is a nuclear machine. Wow, it sounds so dangerous, even though it doesn't have any radioactive material in it. But they had to change the name to MRI because there's no nuclear. But essentially, it's doing the same thing. It's NMRI, right? So, Duncan,
Yeah.
how would you describe NMR?
So it's basically a version of spectroscopy. We're looking at kind of like the time domain response to a spectroscopic measurement. Just to your point about the name change, because it's actually really interesting. Yeah, this was during the the technology was kind of becoming more prevalent during a time, obviously, when nuclear was a pretty politically charged word. So people were pretty scared of anything that was associated. And even though in NMR we're talking about nuclear magnetic resonance, as in to do with the nucleus, um, basically scientists realized that if they were going to get anywhere with the technology, they needed to essentially market it differently. They needed to change the branding of it. So there was a real shift everywhere to kind of change that, and anywhere that you would see NMR, it would be changed to MR or MRI in the specific case of imaging. Yeah, so you even to this day, you see some people moving back. Um, to NMR. I think my thesis I called it NMR, much to I think the chagrin of the director of my MRI center at the time. But yeah, I think there's less pushback on it nowadays. That's for sure.
I see. Because to me, like people who work in NMR, sometimes they don't do specifically the imaging part. They more care more about the instrumentation and such. How can you describe how NMR work?
Sure. So, um, basically, if we want to get an idea about maybe the specifics of the dynamics about how a certain subject works, um, I guess it's easiest probably to go back to like the example of like a hospital, because I think that's kind of MRI as everybody understands it. Um, we want to kind of look at the internals of something without having to get through the exterior. Obviously, if every time you went to the doctor to look up something wrong with you, you wouldn't want to see your doctor getting out the scalpel. So we have lots of different imaging methods for that sort of thing instead. X-ray, for instance, is something that's more like the imaging equivalent of casting a shadow on a wall and then kind of seeing what sticks out. Whereas MRI takes this kind of inherent, it uses the inherent nuclear magnetic moment of like hydrogen atoms within our subject in order to get a signal back. So in the presence of like a really strong magnetic field, in medical imaging, we'd focus primarily on hydrogen. But our subject can be anything. It can be, well, no, not anything. It can be anything with a non-zero magnetic moment. But we could do carbon-13. There's a couple others. But in medical imaging, we specifically want to look at hydrogen. And in the presence of a strong magnetic field, the Boltzmann distribution will tell us that there's going to be like a preferential population aligning with the magnetic field. And the difference in these two populations, the ratio of aligning with the field of like parallel to the field or anti-parallel to the field, is going to give us a net magnetization. So the Boltzmann distribution will also tell us that, you know, the stronger the field or the lower the temperature, the stronger this ratio is going to be, or the higher this ratio is going to be. Basically by manipulating this in our subject, we can get all sorts of different dynamic information out of it, from, you know, the density, the just overall like hydrogen density in localized areas, or dynamic information if we use the right types of sequences.
Okay, so the way I'm trying to explain it to people usually, well, I mean, maybe I'm wrong on this too, because when you have magnets are usually the material where basically the material have a net direction of how, let's go, how the dipole moment align. Like there's like a ferromagnetic, which everything I think aligns on the same into one direction, and a lot of materials can do that, or not a lot, but like metal can be influenced by magnetic fields, so that they're basically the molecules or the atoms aligned magnetically in one direction, creating like this net magnetic field around it. And the material that can do that permanently are magnets, like permanent magnets. But it looks to us in daily life that not everything is metal, right? You put a strong magnet near a book, it wouldn't become attached to the magnet. But I think what MRI is doing, or NMR is trying to do, is we put such a strong magnet that even something that we think has no net dipole moment, like if you think of the water molecule, if you look at the entire molecule, the dipole moment should cancel out, because, well, the physics reason, I think in any steady state solution would have the electrostatic dipole moment of 0. But because it's so strong that individual atom is being affected, that you will be able to align that. And I'm not sure if it's harder. It's probably harder for larger atoms. Like that's why maybe it's really difficult to do like I don't know, like a silicon or something like that. But maybe hydrogen is probably the easiest one because it has the lowest mass, hopefully, and only one proton, even like no neutron, right? So it's easy. And the fact that we can flip that into certain distribution, or flip certain amount of that. And okay, let me put it this way: you can flip more hydrogens, that you can flip more other things.
Yes. Yeah, I think I understand
Yeah.
what you mean. Yes.
So what I'm trying to grab is how did we get signal out of it? Is that the fact that the hydrogen atom is relaxing back to the non-magnetic state that it gives out signal?
Um, so so what we're typically doing is that difference in ratio between the two states is giving us something that we can essentially manipulate. If we have we'll typically have like a radio frequency coil near our subject, and by um, um, imparting a radio frequency pulse at the frequency that we need for the subject, which is determined by the magnetic ratio and the field strength that we're using, that allows us to apply a torque onto that overall magnetization vector that is created by those different populations and the fact that they're not equivalent. The torque that's applied is not is going to kind of knock them off axis. But then when we release that torque, they're going back to that initial state that they want to be in is going to cause a change in magnetic field that we can pick up. It's going to induce an EMF in that same coil that we used to create the radio frequency pulse. So that current that is induced by the relaxation, by it going back to its initial state, is what we actually pick up. That ends up being our signal. So the
When you say
stronger the
current,
yeah,
it's like a radio wave that come out.
it's an yeah, it's a oh man.
It's not like they put a probe. I mean, when you say current, like in a standard, let's say engineering or physics way, it's like like electron moving in a wire, right? But it's not like they're not putting probe into people's body when they do MRI.
No, but the probe will surround them in the instrument.
Right. So it means it sent out like a long range like radio signal that you
Ye-
can measure.
Yeah, so our ability to do the the principle escapes me, but our ability to apply that RF pulse also kind of enforces our ability to receive that same RF pulse in return. So by applying it, we can also get us read that same signal back.
So, in terms of sending and receiving that signal, how sensitive can it be? Like, could you feasibly measure, like, just if you had one hydrogen atom, let's say, in a material, is it sensitive enough to detect I guess, the feedback from that? Or is it a bit more general where you need more to make up for any signal lost? And just as a follow-up question, is the signal that's transmitted when the hydrogen atoms relax, is that randomly distributed in all directions?
Um, so I have to address them one at a time. That's just how my brain
Sorry.
works. That's okay. So to address the first one, the signal to noise ratio for one is like the number one thing you're gonna hear like an NMR scientist talk about in general, and noise is in everything. You're not going to realistically have an experiment where you can detect the induced current of a single hydrogen atom relaxing. This is just because I can't think of a material that wouldn't have its own internal fluctuations that would. It's funny. Before this, I was listening to your episode about with a chemistry student from X, and you're talking about how entropy is the answer for everything, and that's where I'm defaulting to right now. Uh, Basically, as long as you're going to have any level of like background fluctuation in the system, that's what you're trying to beat. And so, as I said before, when you're looking looking to create more signal, you're either looking for lower temperature or you're looking for higher magnetic field strength. So that's, but in terms of limits, exploring the limits, I don't think you're ever gonna get to a point where you can detect a single particle. It's interesting that there have been some forays into using magnetic resonance for quantum states, for instance, as like single qubit, because of your ability to do it that way. But my understanding is that you wouldn't be. I'm not exactly sure how the read write on a on a on an MRI locked qubit works exactly, but yeah, I don't think it's a fun time, that's for sure.
And just to follow up with that, for when the signal's actually emitted, is it randomly in all directions, or is it kind
Oh,
of related to the direction of the magnetic field?
well, it's the signal the signal is the current that's induced by this like oscillating magnetic field. So the magnetic field, I would say, I hesitate to describe it as like in all directions, because that almost like implies there's like a velocity rather than just kind of like a magnetic field flux that is moving.
So during your master's, you used MR pulse sequences to extract information about the dynamics of spray systems. So what do you mean spray systems, and what information did you end up extracting about or from them?
Yeah. Um, so spray systems, I guess, make up more of our lives than you think. Um, you think about an engine that has like a fuel injection system in it. You think about aerosols in cosmetics or irrigation in farming. It's kind of like a system that comes up in a lot of our lives, but it's honestly not something that's well understood. As a process, it's pretty chaotic. So you essentially have a liquid that's forced through a small enough opening, but specifically you're also purposefully introducing kind of turbulation uh, into the fluid that's going to cause like a breakdown process on the surface of the liquid, and that kind of turns into this odd stochastic um, like process that goes from bulk water into just like fine um, um, like droplets essentially. So it's not a process that's really well understood. It's not even really well simulated. So in a lot of industries that rely on this kind of technology, you not really um, you're not starting from base principles. You don't really know exactly what you make in order to get a certain kind of spray. It's more like you make a spray and then you test what properties it has, and you work backwards from that. Um, so the idea kind of was to explore the ability of MRI or MR in general to kind of pull information about the dynamics out of a system like this and see what information we can learn about it. In particular, magnetic resonance kind of succeeds in a lot of areas that other things fail for this kind of thing. So X-ray imaging, for instance, while it's pretty good and is pretty good resolution, it's not going to be able to be useful on materials that are, hard for the X-rays to penetrate. Um, and a lot of these other processes, just like optical imaging that doesn't have any kind of penetration depth, is going to fail for anything that's opaque and enclosed.
And I think the opposite is true too, right? If you have this thing that's too strong, it just go through everything, and that's also useless. X-ray is fortunate enough that it's go through our flesh but not our bones. That's why we can see it. And one thing that well, not one thing. I think I'm still trying to grab more on the NMR stuff specifically because you mentioned is current and EMF and those type of current, but you think about anything that's electricity is an electron thing that's not in the nucleus, right? So how does it relate that we are changing the magnetic field, or we putting magnetic field in? And I think you mentioned the word oscillating magnetic field, which I believe is a secondary magnetic field that we add. Is that the radio wave that you're talking about? Because radio waves also carry magnetic field. And how is that affecting the valence shell, basically the electrons? Because if you're talking about NMR nuclear, that's not electronic, right?
Yeah, rather than affecting the valence shell, the electromagnetic pulse is just is it's an the RF pulse is an oscillation. It's an EMF itself that's just being emitted perpendicular to our strong magnetic field, and by right hand rule, we're just getting a force that is applying a torque onto all our individual little, for instance, hydrogen, um, our little hydrogen bar magnets in this case, and the fact that we have that disproportionate ratio is just resulting in an overall like aggregate result.
Right. Oh, so it's not just affecting the nucleus; it's affecting the entire atom. Right. So if
Yeah, exactly.
yeah,
And then it's the
okay.
total behavior. It's the behavior of the system altogether, that is like essentially causing a statistical, what appears to be a statistical or like individual action.
Right. So even though it says specific nuclear, because if I think of nuclear interaction, I would think of
Mhm.
something that all the major thing is about affecting the nucleus. But in this case, it appears like it's affecting the atom itself, right? The dipole moment is come from the fact that it has electrons around it too, right? Like plus
Yeah.
and minus. So it's weird to me that the word is nuclear, while in a practical sense is affecting the magnetic field of this aggregate group of hydrogen atoms.
Yeah. Yeah. No, and that's the understanding of MR as a concept has been misunderstood, um, like a lot. Even some of the people who were the first ones to create the techniques that we use to this day for really simple measurements, um, were misunderstanding, um, exactly how the process worked, and which is ironic, I think, because I'm not doing an amazing job of describing the process itself. But um, yeah, like CPMG, which is one of the most often used techniques for MRI. The C in CPMG, I think, Carr, um, thought it was a driven process for the longest time, but since then we've discovered it's not. So it's not something that has been obvious for a long time at all.
Yeah, that's not a super uncommon thing in physics. I think. I mean, even maybe I'm remembering this wrong, but even like electro motive force EMF was like originally, it's not a force, it's the voltage or a potential, right? Um, and I think back in the day, many moons ago, people misinterpreted it a little bit, and it's just kind of kept that name since. But going back a little bit, so you did a physics degree, but
Yeah.
you ended up kind of, I know at our undergrad university, there was nobody directly in the physics department who did, or maybe I'm wrong, but I don't think there's anyone who did like MRI physics or NMR physics.
No,
You ended
no.
up working for Dr. Levman. So how did that end up happening? Like, how did you get into that at X? And um, what was this kind of biomedical MRI data you were looking through? I'm guessing it had to do with the brain because I know his group did a lot of like brain imaging with MRI data, I think.
Oh, actually,
Yeah.
before we get to your background stuff, just I think one last
Oh,
thing.
we're running out of time, Pheely.
Yeah. Why is NMR safe?
Ah,
Where you're flipping bunch of, add hydrogen atoms in your body with really strong magnetic field. It feels like, oh, it could be dangerous. Why is it safe?
Well, most of as long as the frequency of the applied like pulse of the process is not going to heat you, that's basically the only safety concern to begin with. Um, the presence it's interesting because it's not a insanely well studied area. But the to my knowledge, the presence of a strong magnetic field on its own is not inherently dangerous. But that being said, my lab was mostly um, uh, non-biological studies, so I was not putting my arm in the magnet when I was running experiments. So might have to hope for a medical physicist guest for that one.
How powerful were the magnets that you were using for your research?
Um, so the bore, keeping in mind that the size of the bore, which is kind of the the area that you have to work with is not huge. I would say it's probably like 4 inches in diameter, and then maybe the because the area that we only care about really is the area that has a steady, consistent magnetic field strength. But 4.7 Tesla was what I was working with. Um, which is pretty strong to put it into context, I guess, for something that's outside of just numbers. Um, you absolutely knew if you had forgotten to take something out of your pocket when you were anywhere near the magnet. Like that's for sure. And like you're giving it you're giving it at least like 5 feet of berth in every direction um, for approaching it. Um, Pat downs in our lab were very, very, very common. You you walk into the lab room and you're checking every single pocket you have.
So, all right, the way I put in terms of safety is that almost everything that we deal with in daily life are chemical reactions, and chemical reactions are all dependent on electronic structures of materials. While NMR changed basically the direction of a dipole moment, it has done nothing to the electronic structure in terms of interaction. So it wouldn't change any chemical interactions in your body. It wouldn't change anything else at all, right? And once it's gone, it just relaxes back. And that's pretty much it. That's why I think it's safe.
yeah, and the forces in molecules are pretty strong, right? Like you think, 1/r² laws. Like these things are very, very close together. So on very short distances, I think you get pretty powerful forces that bond them together. So probably hard to kind of separate them.
Yeah.
Just
That
like with a
being
magnet, I guess.
um that being said, I definitely had experiments where you run the pulses for too long, longer than you mean to, and your sample comes out a little toasty hot. So that is obviously being taken into account. Just to be clear, when we're talking about like medical uh, applications, but I guess the upshot of working with samples that you know don't have a brain is is that you don't have to worry about that sort of thing.
And also, like, you know, well, then what's the take home message? It's not going to make you radioactive. It has nothing
No,
to do with
oh
that.
no, yes. If yeah, you can take away anything is that I have heard people say they're like concerned about how much radiation they'll get from an MRI, and you don't have to. Yeah, don't worry about that. You can safely put that one to rest.
All right, back to the original question. So, what was what got you into that MRI stuff during your undergrad? Because you were doing like a physics degree, and I don't know what you were interested in when you were doing that, but at some point you decided to go work for Dr. Levman, who's not in the physics department.
Yeah.
So that's
Yep.
like a nice little collaboration there. So, kind of what got you into it, and how'd that go?
Yeah, so I think I was just really eager to do research at the time. I'm not sure if I think it's a pretty common story among students is just rather than like for some people, I guess they know what they want to do research wise. And for me, it was just that I knew I wanted to do research. Um, and so it was kind of appealing to me that there was somebody who was kind of um, physics adjacent, I guess you would say, in in our building. So I reached out to Jacob, and um, he gave me a job for the summer looking into different ways to reconstruct MRI image data. So it was really interesting prospect, and I had a lot of fun doing it. The idea was basically that we had the data for um, that had been taken from like raw from an MRI scanner, and we wanted to see how we could reduce the information into ways that would highlight different different aspects of the brain. Um, it was really open ended, which was something I really liked because it gave me the flexibility to try very out there things. And ironically, I think in retrospect, there are things that I tried and ended up giving interesting results that, with a background in magnetic resonance that I have now, I would not have bothered pursuing, which is kind of an interesting way that went. There's something to be said for kind of letting someone tinker with something they don't fully understand, because the the more you understand a topic, sometimes you rule out something because there's a perception of understanding. Um, so working with that, we ended up having some pretty interesting work um, that was able to highlight some like interesting brain regions.
Yeah, no, I definitely feel that when it comes to research that it's like, what how did you get into what you're doing? It's like, well, there was an opening and I wanted a position. That's kind of how I got into what I'm doing as well. It's like I just found a guy who did it and said, "All right, I'll work for them." Um yeah, and it's cool. You kind of just go with the flow, and next thing you know, you're working on river class destroyers, I guess, right?
The
Yeah.
Yeah, the inter that's one through line, I guess you could say, is the interdisciplinary aspect has been
Mhm.
one thing that's been the whole way through. Yeah.
Yeah. Was it difficult to transition from academic work to like industrial work? Like, was it you find a nature like research? I don't know if it's more or less pressure for you in terms of like, you know, is there more because research is like we are looking to find things the unknown, right? Sometimes it doesn't work, sometimes it works. We try to develop a technique to find something new. While a lot of times when you have an engineering goal or specific goal, it's very like rigid. It's like, okay, we need to build this, right? This is the goal. We have this is the product that we want to create. It's like, do you find that type of this environment different?
The environment is, yeah, very different, I would say. Um,
Was it
so
difficult to transition?
I would say I would say it was not a difficult transition because if anything, I there's an anticipation that I had for going into the workforce after kind of a physics academia experience that there would be more deadlines, more pressing deadlines, and a more expectation to go above and beyond. Um, kind of all the time. Academia has a way of getting into your head and constantly kind of putting a voice in your head that's telling you you're not running fast enough, or at least that's my experience. Um, and moving into the workforce has been kind of different. It's kind of like I realized that I'm still in a sprinter's mindset, and everybody is kind of set up for long distance, and
You realize help workers, right?
your words, not mine. but,
I, I will say, especially in government jobs, that seems to be the experience of like, oh yeah, we can take our time.
Yeah, 100%. Like, yeah, when you work for the government, it's, hurry up and wait, right? It's obviously not the truth, but that's the joke they say. Things move a bit slower with government jobs typically. I don't know if it's the case for you, but there's a lot more like kind of paperwork and legal things that need to be done. So it takes a bit more time. And yeah, there's like, you're not academia is kind of brutal in that sense where people exploit people a lot. They're like, all right, I've got these guys working for me. I'm going to milk them. Going to get every drop of juice out of them I can.
So to get a little bit deeper into your background, what got you into science and physics? Or were you always a kid who were into science, or you picked it up in high school? What interests you into going to physics, which is kind of a niche field? It's not the easiest thing to study in college, right? And what got you into it?
Yeah, I would say physics for me was less of it wasn't a high school passion. It was more like it was I've always been fundamentally interested in kind of understanding the world around me. And it was kind of a catch-all because physics brushes up against everything else, basically. You're gonna find a bit of overlap with physics and every scientific concept that has, interesting phenomena or something cool about it. Physics to me was a way of kind of touching all of these things at once and kind of enabling my own curiosity about the world. From background way back, yeah, I always liked science, and I think my dad instilled like a love of science fiction and that kind of thing in me. So um, yeah, that kind of transferred into you want to do something that is at least tangentially related to what your interests are, and to me, going with physics was ensuring that at the very least academically, I was going to be doing something cool.
So, what was the core science fiction that you held dear when you were young? What was the that one fiction?
Oh, that's tough. God, it's tropey. Probably something like Star Trek or something like that. My dad loved that stuff. It would always be on the television. Next Generations, if I had to pick one.
Nice.
Nice. So the one thing that we always ask every guest, and this one loaded question that we always ask is what are your hopes and dreams? Where do you see yourself working, or who do you see yourself be? Do you see yourself keep working on these type like of government work, or you see more maybe go to a more engineering type, back to academia? Do you still want to come back to NMR? Do you want to be a scientist, or what are your hopes and dreams?
Um, wow. Yeah, it's hard to say exactly where it's going to manifest in my life, but I think the one thing I can say with certainty is that I'm gonna continue to do things that challenge me. I think the most important thing for me, and like anybody in physics will understand that it takes a certain amount of masochism, I think, to push through and understand that you have to find a little bit of like pleasure in the pain, because otherwise there's not much. um, yeah, so I think that's going to continue through, and I'm always going to be trying to find something that maybe frustrates me, but comes with that aha moment that keeps you pushing. I don't know if that's always going to take place as a career choice or as a hobby, but that's always going to be there for sure. And as long as I can keep doing that, I think I'm going to be satisfied.
Nice. It's like that. I don't know. Is it like a proverb or something? We always, we stumble when we make a journey uphill, right? It's part of it, and a lot of research is stumbling, unfortunately. Because sometimes it's not as obvious what we're gonna find, and that's the challenge. And sometimes you doubt yourself. It's similar to I think writers, right? Like someday you might wake up and you can't write a word. There's no paragraph. You think if you have any talent at all, why do you even start writing? Painters or people who draw, one day, someday you just can't draw well. And in research, sometimes it's really difficult to go to work and not find anything for the past week, or it could be months or two.
Yeah.
And sometimes that eureka moment might be extremely hard to find.
Yeah. Absolutely.
Well, thank you very much for joining us, Duncan. It was great to have you and catch up on your work. And I think the last time, at least Pheely and I saw you, was at CAP in 2022 at the Canadian Physics
Yeah.
Conference at McMaster. So, like, we haven't seen each other in a while, and it was good to get an update and catch up. So, thanks for coming.
Yeah, thank you for having me again. You guys have an awesome show here. I really appreciate the work that goes into it too, and thanks for having me.
Oh, thank you so much. So, before we end the episode off, Patrick, how are people gonna reach us?
Well, that is an excellent question, Liam, and
Only the best.
one which has many answers to it. Well, at least a few. So, the first way that you can contact us, whether you have questions about the show, or if you would like to be a guest on a show because you're an expert in your area, you can reach us through email. We are hyperthesispodcast@gmail.com. You can send us an email, which we are pretty good to check, and we'll make sure to respond to you. We love having questions or even episode requests. If you're like, oh, I really want to know more about this topic, then let us know and we might be able to make that work for you. If you're more modern or hip with the times, I guess, feel free to send us a DM on Instagram. We are at the Hyperthesis. We also send posts of when we post these episodes, along with some behind the scenes looks and some memes and other things. So follow us on Instagram, and I guess you don't subscribe on Instagram, but you can give us a follow. If you are interested in contacting our guest today, Duncan, what would be the best way to do that?
I think the best way would probably be to contact you guys if they have problems, and then they can percolate back to me.
Fair enough. So if you do have questions for Duncan, feel free to send us an email and we will make sure your question gets asked, and provided it's appropriate, I guess. If you're listening to us, you've found us, congratulations. We are based out of Spotify, but we are found on pretty much any podcasting service that you can use. So make sure, if you're able, to leave a review or even just a rating. Let us know in whatever podcasting app you use what you'd like to hear for episodes. And you can also find us on YouTube. We are just newly releasing our season 7. So I think we've only released a couple episodes, but at the time of this recording, but we'll hopefully be getting our YouTube caught up. We'll see. And you can like, subscribe, comment, share there as well. So share us with your friends. Let us know if you have questions either for us or for Duncan. And if you're interested on coming on the show, like all the guests that we've had so far, who have all been excellent, feel free to reach out to us and let us know what your area of interest is.
All right, Patrick. And now, thank you for that. But now for the story.
All right. So this is a story I've told a few
it's Pheely.
times.
Whoops. Some reason I forgot that you're telling the story and I introduced Patrick. All right, Pheely, the story. Thank you.
Yeah. So now, and see, Liam, how you joked about I got it wrong last time you told a story. I was like, oh no, it's not Patrick, it's Liam. Yeah.
All right. You
But
know what?
since I'm a better man, I'm not gonna comment on that.
That's too late.
so-
You already did.
Hey, I'm the editor though. The false narrative can be forged, but I won't do it. I will leave all this in. So
You're good.
this
You're a
is a
good man. Better
story.
than I would be.
This is a story I've told a few times in the conferences because I think my master works was on some warship design, and one of the cautionary tale in warship building is this failure. Or some wouldn't say failure, but compared to original goal, the Zumwalt class destroyers that were built in the United States there were a lot of problems, and some could say it's engineering problem, or could be more bureaucracy, could be all these big picture problems. But I'm gonna go into a little bit of the history of it. So after the World War II and during the Cold War, everything there's a lot of scientific development, and one of the major change is that everything is kind of going electric. Like now we can see a lot of electric cars, even electric ships around, and the idea of having electric warships has been around for a long time. But to realize that into actual ships are taking a lot of time. And in the 80s and 90s, there were this idea to transition from, the idea came before that too, is that battleships are this biggest class of warships that they had at the time, and they were, equipped with large guns, can shoot kilometers away. However, they're so large that like it's gonna take a lot of resources, and also it's so large that with the development of missiles, it's almost like it's gonna sink if got hit by one missiles. And the fact that we have missiles that can shoot much further than guns quite very accurately makes the battleships obsolete. So if you see the ships in the Navy, almost most places now they contain like cruisers and destroyers and maybe aircraft carrier. None of these, except for the carrier, are quite small compared to like the battleship with large guns, and things are moving towards missiles instead. So the idea in the 80s and 90s was having this electric ship that basically have small radar cross section, so have this stealth capability, so to hide from all this detection and such. And the timeline was quite long, maybe like 1 or 2 decades to design, develop, and build. However, the fact that the design parameters are quite large, like there's a lot of things to consider, the timeline is quite long. One of the problems is that auto technologies catch up. So the ships, the warship of Zumwalt class was ordered in 2001 of 32 ships to build 32 ships on billions and billions of dollars. So the idea is to have these small electric ships that's like not that small but stealthy. It would be the destroyers. So the destroyer, one of the smaller class of the warships, where it acts like a destroyer to destroy bigger ships using what they had back in the World War II, would be like torpedoes and stuff. But now they're all usually missiles. So the thing about stealth capability is that the development of the radar and detection technology has become so good that it's almost like impossible to evade detection when you're at that size. So even though the things are ordered in 2001 to develop and to build, hopefully when it's done, the idea of the stealth capability was dropped in 2008 because they realized that the radar these at the time was good enough to detect a small fishing boat. So there's no way that it's gonna evade that. So there'll be things that change along the way. And the development of the gun ammunition that would go into the ship was developed starting in 2005. So the flagship was started construction in 2009, so 8 years after all the development, and it's finished the construction in 2013. But by that time, they have burned so much money and research and development resources that I think they reduced the number. Instead of oh, we ordered 32. Well, we are broke now. They're not broke, but they went way, way over budget that they're not building 32 anymore. So what happened is that, well, okay, we have this ship that were built and constructed, the flagship in 2013. Well, but the ammunition wasn't ready. So they had this empty ship, with a gun with no ammo that's floating around that cannot be used. And in fact, it turned out the ammunition got too expensive and to make and to use, so they discontinued the ammunition research and development in 2016. So in fact, they had one flagship that's really have no guns. And the other idea that they wanted to build on it is that since it's an electric ship, maybe railgun would be really good, right? Railgun runs on electricity, on magnetic and electromagnetic force. Well. By the time that 2021, railgun has been discontinued so far. It might come back up again in the future, but from my understanding is that even though they can make a projectile that go very fast, shoot target really far, sure, but because the momentum of the bullet, basically, there's almost no barrels that can handle the rail gun. So it would happen like, well, it's not that we can't make rail guns. It's like if you shoot like maybe 10 times, the barrel's gonna explode, and so there's this problem. So rail guns also have been shelved. It begs the question. Now we have this very expensive ship that we thought we were gonna build 32 of them. We built a flagship. There's no ammo, so it's based almost a useless ship. So what happened is that this idea of the hypersonic missiles that came in 2017 kind of give this project another hope. Well, and it's fortunate that what they were designing for the hypersonic missiles at the time fits into the hull of the Zumwalt class destroyers, barely. So they start repurposing to do that. So they ended up build 2 more ships. So it ended up 3 ships in total. But the order was 32, but since they went way, way over budget, they can only build 3 ships. And the ships are actually, if you look at the design goal when it was proposed, stealth, no. Gun and ammo, no. Railgun, no. So like none of the parameters that are set as a goal were achieved, and now they're gonna probably try to put in the hypersonic missiles that will be developed. Hopefully, we don't know about that either, right? So this is kind of the short cautionary tale of this type of long-term development, where sometimes you just don't know what's really gonna happen, and other things that you cannot control is other types of technologies are being developed a lot in parallel to your ship design, for example, that really render the technology that you're trying to make obsolete. So I don't know what's going to happen to River class. I hope they learn from the U.S. this debacle that happened. And when I heard, they ordered 15. Well, who knows? For the Zumwalt and with the budget of the U.S. military, which is extremely large, right? They can only build 3 out of 32. So I don't know what the development timeline is gonna be for the River class, but from what I see from history, I hope they learn the lessons from other people's mistakes, and we got the actual 15. That's the story for today.
Well, very interesting. Thank you, Pheely. Yeah, it's you think of how much has changed in 20 years, right? Like it's so many technologies have advanced so rapidly, especially like computers and um just so much, right? Like microchips and everything, and and if you've designed this ship in the early 2000s, then like by the time you reach 2020, you're gonna realize like so many things are outdated and could be way more efficiently replaced. But is it worth doing it? Do you just keep things? So it's all very interesting stuff. And yeah, I'm sure people have learned from their mistakes, and at least they're trying to like account for this stuff in the modern day shipbuilding world. Although, who knows? Not me. But all right. Well, thanks again, everybody, for tuning in. Thanks to Pheely and Patrick and Duncan. It was a good time. I learned a lot.
All right, thank you. Take care.
Thanks.
Bye, everyone.
See ya.